Hello everyone, and welcome back to the Fluctus channel. While the United States Marines are indeed a part of the U.S. Navy, they have very different needs and perform very different missions. So when the highly versatile F-35 Lightning II was introduced, both parties were very eager to see what it could do. There are several variants of the multi-role fighter. The F-35A is the conventional takeoff and landing model. While the F-35B is a VTOL, or vertical takeoff and landing aircraft. By changing the direction of its thrust, the F-35B can take off, hover, and land much like a helicopter. It can also use this system to perform short takeoffs and landings, such as those using a ski jump ramp as exercised by the UK Navy. In 2020, the HMS Queen Elizabeth hosted the U.S. Marine Corps F-35B as part of a joint exercise between the U.S. Marines and the Royal UK Navy. The goal was to investigate how well the B variant could operate from an actual flight deck with a ski jump ramp. At the Patuxent River Air Base back in 2015, the F-35B was tested to be able to take off horizontally using a ski jump ramp from a runway length, replicating the expanse of an aircraft carrier flight deck. However, alternative tests were later performed aboard the USS America, an amphibious assault ship that lacks many of the flight deck characteristics of an aircraft carrier. In this case, the F-35 would need to take off without the benefit of a ski jump. This explored the use of both the aircraft's vertical takeoff and short takeoff capabilities. For the Marines, these are essential to the F-35B's ability to be combat effective and versatile, regardless of whether it's deployed on land or at sea. Across the Atlantic in the United States, the U.S. Navy has instead embraced the F-35C. This model was designed to utilize the special cattle bar system at the heart of carrier flight deck operations. Among other things, the F-35C boasts larger wings to help enable increased range and payload, while also allowing for increased low-speed control. To save space when stored, the tips of these wings can fold up, narrowing the overall width of the aircraft by several meters. It also boasts a tailhook to engage with the kettle bar while landing, and reinforced landing gear to aid carrier-based operations. Despite all of these modifications, the F-35 remains one of the most versatile and advanced military aircraft in the current market. It's also intentionally designed to be upgraded as technology advances, allowing everything from sensors to avionics to be improved as needed. The F-35C has only been operating via aircraft carrier since 2019, and there's little doubt it has a bright future in sea-based operations. At the end of the day, the ability of high-speed military aircraft like the F-35C to take off and land on an aircraft carrier flight deck hinges on the Catapult system. The acronym stands for Catapult Assisted Takeoff but Arrested Recovery. As the name implies, the system utilizes a steam-based catapult to help launch aircraft into the air. Flight deck runways are much shorter than those found on land, so it's imperative the aircraft reach minimal takeoff speed in just a few seconds. During operation, an aircraft is positioned at the front of the catapult, where a tow bar near the landing gear attaches to a shuttle. This shuttle is what moves when the catapult is fired, pulling the plane forward at high speed. Flight deck crews will also raise a blast shield behind the aircraft. This protects personnel and equipment from the jet blast. Each catapult is powered by a steam engine and piston setup. Prior to a launch, steam is collected and pressurized inside an accumulator tank located under the flight deck. The steam is monitored by a special flight deck officer known as the shooter. When ready, the shooter releases the pressurized steam and sends the aircraft forward at around 165 miles per hour. Though it is technically part of the same system, the arresting part of the Catapult design utilizes an entirely different mechanism. At the stern end of the flight deck are 3 to 4 cables, or arresting wires, that are stretched out across the runway. Pilots are required to catch one of these wires with the tail hook that's attached to the rear section of their aircraft's fuselage. That's why planes landing on aircraft carriers assume a precise angle, putting the nose up and the tail down to engage the hook. Once the hook catches, the kinetic energy of the aircraft has to be absorbed in order to bring it to a safe stop. The cable does this by transferring that energy to a hydraulic system located beneath the flight deck. Essentially, the end of each cable is attached to a cable and pulley system attached to a hydraulic cylinder. As the plane's arresting hook pulls up on the cable, the cylinders engage, using the resulting pressurization to bring the aircraft to a short and safe stop. The Catapult system is the only launch system that has been researched by the U.S. Navy. Recently, the EMALS Catapult, which stands for the Electromagnetic Aircraft Launch System, was installed on the USS Gerald Ford. Testing was done utilizing particular deadload objects, which simulate the weight and feel of a real aircraft. These objects are simply hooked up to the EMALS Catapult in place of a plane, then flung into the sea before being recovered. In recent years, the Navy has become more and more convinced that the EMALS system is the wave of the future. This type of catapult utilizes a linear induction motor instead of a steam piston. The newer system weighs less, accelerates aircraft more smoothly, and can launch heavier aircraft than the Catapult. It also costs much less to operate and maintain while drastically reducing the carrier's freshwater usage. Indeed, Arrested landing systems are primarily the domain of aircraft carriers. However, in recent years, air forces worldwide have started exploring the concept of land-based arresting cables. For instance, such a system could be utilized to speed up aircraft recovery time by reducing the amount of runway needed for the plane to come to a stop. It also has potential as an emergency measure for when planes are unable to come to a safe stop due to damage or malfunction. These systems are very similar to those used aboard a ship. Instead, transferring the kinetic energy to two large hydraulic reels located on either side of the runway. Though the system is still being tested, it may serve as yet another example of how two very different military branches can learn from one another's tactics and engineering strategies to create a safer, more efficient operational environment. That's the end of this video. I hope you enjoyed it. Make sure to subscribe to this channel so you don't miss any of our new content. See you next time.